Can you hear me? Good. Can you hear me now? No? Yes. You heard me? Okay. No green? Yes, green? I don't see. I'll go closer to see. Let's test. No green. I don't see a green. I don't know. Not for me. Yeah, it's here. No, it's not from the light. Sounds like an alarm. This is like maybe it's not in here. Maybe it's in some of the rooms above.
Okay, welcome to the next session. Let's get started. My name is Per Kraus. I'm a faculty member here. I'm also the Associate Director of the Baumik Institute. And so here we also, I'd like to wish Manny happy birthday. And you're too late, but also express my personal gratitude for your generosity in funding pure research here at UCLA, which is a very rare and precious thing. And it's made a huge difference here before and after. So thank you so much. And I'm now happy to introduce Smadar Naoz, my colleague in the department. She's the Howard and Ostrid Preston Term Chair in Astrophysics. Smadar received her PhD in 2010 from Tel Aviv University. She then had a postdoctoral position at Northwestern, followed by being an Einstein Fellow at the Harvard Smithsonian Center for Astrophysics. And she joined the faculty of UCLA in 2014. She's received many awards for her work. These include the Annie Jump Cannon Prize and Helen B. Warner Prize from the American Astronautical Society, and a Sloan Research Fellowship, among other things. And let me also add that Smadar is a tireless contributor to equity, diversity, and inclusion here at UCLA and elsewhere, and is really, I'll just speak to the leader of that here at UCLA, so we're all very thankful for that. And today she'll be telling us about gravitational wave sources at the heart of galaxies.
Thank you. Thank you very much, and hi, everyone. And I want to begin with wishing Manny happy birthday. And I really want to tell you that your vision and generosity really transformed our department. So thank you so much. Birthday. And in this talk, I'm going to talk about gravitational waves at the heart of galaxies. And I'm going to show you that the centers of galaxies, where we find the supermassive black holes, these are natural places to find gravitational wave sources. In particular, I will, my laptop froze, of course, because why not? All right. In particular, I will show you what are some of the challenges that we need to have, or that we have when we try to merge two black holes together. And then I will try to motivate how we can understand the LIGO sources that we just heard about. And I will cover both black holes, big and small. And throughout my talk, I will I will motivate I will talk about what the future holds, and I will also give predictions of what we expect to see. I want to start actually by describing the general idea of how we work. At the end of the day, it all boils down to solving Einstein equations, where we connect Einstein tensor with a stress energy tensor of the matter field. And the point is that we're looking at gravitational wave emission as indicators for black holes. So if you like to think about this, if we're thinking about particle physics, which is not something that I work on, and we want to be able to detect those particles, we need to see them somehow. So here, our way of seeing those black holes is through gravitational wave emission. And we're working on, in astronomy, unlike accelerators where we have a controlled experiment, in astronomy, the experiment is not controlled. Nature doesn't give us anything controlled. And we're working in a very complex system. So we're going to use perturbation theory in this complex system, where in the weak field, we will use Newtonian approach, and we will use general relativity when needed. Now, I keep on saying we. I want to present you my group. I work with a lot of people. I'm having fun with my group. We're working, we're covering a wide range of topics, from cosmology, the first galaxies, all the way to black holes, stars, and even planets. And there is one thing that connects them all, which is physics and gravity at different scales. I will not be able to talk, of course, about what all of them are doing. I would say that about 45% of the personnel in my group work on gravitational wave related works. And we were fortunate that about a couple of my students received a partial Baumik summer funding. So thank you, Mani. And I want to highlight Erez Michaeli, who's a postdoc, who's also partially funded by the Institute. And he started in the fall, and he just had a paper about black hole neutron star mergers. So again, thank you so much, Mani, for it. And here we're kind of professional looking, more or less, but sometimes we just like to eat together and even sometimes work. So, all right, but let me start. And I'm very happy that we had the talk from Ari before, because gravitational waves really transform the way that we sense our universe. We now have a new way to feel it and see what is happening around us. And LIGO has observed so many things. So here I'm showing in the y-axis, you can see here, this is the mass in solar mass of things that were detected. The x-axis is arbitrary to make this butterfly shape. I didn't make that. You can see here the blue are the merger products from LIGO. So these are black holes that merged. The red are black holes that were detected through accretion disk flowing onto a black hole. So these are called electromagnetic detections. The orange are neutron stars and detected via LIGO, and the yellow are neutron stars, again, with accretion disk detection. And maybe there are many things to take away. For example, we can see here that there's a big gap, the mass gap that Barry talked about. But maybe one of the other things that to take away from here, which is amazing, is the fact that there are so many black holes. In fact, LIGO estimates that almost every 15 minutes, we have 2 black holes merging together in our local universe, which is pretty impressive when you think about that. And it's even more impressive if you realize that before LIGO made their detection, most people working on the topic would not have thought that LIGO will see black hole mergers in such high frequency. In fact, some people bet that they will see exactly 0. So I want to explain, at least heuristically, what are some of the challenges that we expect that black hole will merge with another black hole. So I'm going to describe a heuristic recipe. So I need a chef. By the way, I like to make jokes in my talks. I know I'm not very funny, but bear with me with all my jokes. So I hope at least that you can smile. I cannot see because you have masks. And I also need 2 stars. So we think that those black holes that LIGO sees are the end results of massive stars, more massive than 30 times the mass of the sun, that end its life with a black hole. So I need two to create two black holes and merge them. And the first question may be, are two stars something that we expect? And yes, we do. We expect a lot of binary stars, pair of stars. This is Tatooine from Star Wars. We're near Hollywood, so that makes a lot of sense, right? However, of course, nature may throw a wrinkle at us and say, oh, that doesn't work, but it does. In fact, most stars love to live in binaries. Our sun had a 50-50 chance to have a companion. And the massive stars, those that we expect to form black holes, most of them, if not all of them, are born in a binary configuration. So that works. Okay, so now we established that we can have two stars. As stars evolve and exhaust their hydrogen supply, they start to expand. So let these stars expand. And what happened here is that I drew these two stars a little bit too close, and they start to overlap each other. And we see things like that in nature. And because they overlap, the end result is one star and therefore one black hole. So that's not very good because I wanted two black holes to merge them. So you can say, okay, Smadar, the solution is very clear. Just draw the two stars further from one another. They will evolve, will go through midlife crisis, become fatter a little bit, larger. They'll lose some mass. They'll have a supernova, become two black holes. Yay, now they can merge. However, calculations prior to LIGO's detections suggested that in order to merge, in order to overcome the overlapping part, so they will not start to eat each other, you need to put the two stars and therefore the end result, two black holes, so far apart that they will never merge within the time of the universe age. So that was the problem. And this is why many people thought that we will never see anything with LIGO, at least not black holes, black holes. The main idea was to look at neutron stars, in fact. So somehow we need to help black holes to merge and find each other. One of the ways that people are thinking about is to help them in dense stellar cluster like globular clusters. These are dense star clusters, very old. They have stars and stellar remnant. And in these places, you can have three-body interactions. These are resonant interactions where I have two binary black hole meet another black hole. I create a new binary, and then again and again and again. And each time that this is happening, I shrink and shrink and shrink the separation until they merge. So here in this movie, which I'm going to fast forward a little bit, you can see here it is. This is the red product. This is the black hole that was created. And that seems pretty cool. There's a lot of interesting physics too. I will get to some physics about the triples in a second. And here is also a snapshot that you can see here for the resonant interaction here. But we were thinking, well, if we're thinking about dense star clusters, why not think about the densest of them all in our local universe, which resides at the heart of galaxies. So let's talk a little bit about the heart of galaxies. So we know that almost every galaxy hosts a supermassive black hole in its center with masses between million to billion solar mass. And surrounding these supermassive black holes are stellar structures of stars and stellar remnant like black holes, neutron stars, and white dwarfs. And that means that, like in this movie, a particle or a binary feels not only the interactions and the gravitational pull of the supermassive black hole, but also of many, many neighbors. So from a dynamics point of view, this system is rich and very interesting because many things can happen. And luckily for us, we have a supermassive black hole in our backyard, where detailed observations found that its mass is about 4 million solar mass. And that yielded the Nobel Prize of 2020. And I want to highlight Andrea Ghez from our own department. We're still in celebration mode. We're actually going to have yet another celebration on Thursday for her. So we're very excited still because it's such a great honor and she very well deserved. So detailed observations of that place combined with theoretical arguments suggested that this place, even though it's very complex and very dense, should host binary stars. So if I have binary stars, I should have binary black holes, and we can try to see what will happen to binaries in general in this place. Okay, so here is my theorist impression of binaries at the galactic center. This is not to scale, of course. Here I have the two maybe black holes, smaller black holes, and this is the supermassive black hole. And my question is, will they merge or not, right? I want them to merge. Okay, but this place I said is extremely dense. So let's see what happens in such a dense environment and how dense is it, right? It's not good enough to say something is big with respect to what. So let's think about for a second on our sun and our closest neighbor, which is about 1.3 parsecs away. Between us and the closest neighbor, Proxima Centauri A and B and Alpha. By the way, it's a three stellar system, which is kind of cool if you think about that. But between us and our closest neighbor, there is nothing. This is it. But if I'll draw a similar volume around the supermassive black hole at the center of our galaxy, I will find that there are a million stars there. So this is how dense this place is. That means that the binary live in that place will undergo multiple interactions with neighbors. And these interactions are accumulating, and as time goes by, it will unbind the binary. So now you can think to yourself, hold on, that's very confusing. A few slides ago, you talked about globular clusters. You had a binary interacted with another single, and then you got that you shrank the orbit. Now you have a binary interacting with a single, and then you unbind the orbit. So decide which one is it. And the answer, it's both, because it depends on the velocity dispersion of the cluster, so how fast things are coming, and also how far away my binary is, how wide it is. Because I want, remember, to start with a wide binary to overcome that overlapping space. So I'm starting in the galactic center with wide-ish binaries, and I'm saying wide-ish because it depends on all your assumptions of stellar evolution, blah, blah, blah. But we start with this, and then we can estimate how long it will take to unbind the binary. And this is work that was having some corrections to what was taught before, was led by one of my students, Sanaya Rose. So we are going to take that into account in all of our calculations. And interestingly enough, it takes time to unbind binaries. So now let's look just before they become unbound. So here it is again. And the way to actually get these binaries on a stable configuration, meaning that they will not be disrupted by the supermassive black hole, is to have a binary, to have a pair on a tight configuration like this. And what happened is that they will orbit each other's center of mass. And together, they will orbit the supermassive black hole, or the three-body center of mass. And this process, this type of system, the three-body system, it actually has a long history in physics. It's a fundamental question in physics. Dates all the way back to Newton when he considered the Earth, Moon, and Sun system. To Poincaré, to Lagrange, many people have studied this. And specifically, this separation of scales, where you have something moving on a short period and another thing on a longer period, this had been studied specifically by Kozai and Lidov separately in the 1960s. And the idea is as follows. What happened is, on a short time scale, orbital time scale, the system is kind of boring, right? They just orbit each other. And since they orbit each other, I can actually separate the scales very nicely. So here I'm writing the Hamiltonian, separated in scales. The first part I can identify as the part of the inner, this is the Kepler energy of the inner orbit. Then I can have the Kepler energy of the outer orbit. And the final term, this term, is an expansion. These are Legendre polynomials that take place because I have a tight orbit over a big orbit. So it's the separation one over each other, which is a small parameter. And I can treat it as an expansion. By the way, does anyone see something funny with this Hamiltonian? There's something funny here. Maybe the students want to say something. that we just finished our quarter, so I'm still in with my instructor hat. If you notice, there is a minus sign in this Hamiltonian, right? We're working with bound systems, and yet I'm writing here a positive Hamiltonian. It's an interesting notation issue in dynamics and astrophysics, and I can tell you that it has led to many mistakes in the literature of a minus mistake, and then things move to the wrong side, and that's a problem. Okay, but we can remember now in our head that there is a minus sign and treat it accordingly and do it well. A system like this was studied by Kozai-Lidov, I said, and what they have said, they said, okay, you know what we can do? We can take those fast-moving angles and we can eliminate them from the Hamiltonian. Effectively speaking, what they do is you smash the mass around the orbit and you treat these two orbits as two wires that interact with one another. This is called the secular approximation, if you've ever heard of it. And what Kozai, for example, showed, this was also done only with pen and paper, which is pretty impressive. He showed that if you start with sufficiently inclined system like this, the inner orbit eccentricity, meaning how elliptical the system is oscillating with inclination, how inclined it is with respect to the other orbit. It does something like this. We have oscillations back and forth. When it's more inclined like this, it's more circular. And then when it's less inclined, like it's about to become, it's going to be more and more eccentric, like that. And he also found something that he called the integral of motion. Until this day, sometimes people call it the Kozai integral of motion, that can be written like this. This one is the angular momentum of, this is the z component of the angular momentum of the inner orbit. So it's projecting this one on the total angular momentum. The total angular momentum in the system is conserved. This is a spherically symmetric system, so it's conserved by definition. It makes a lot of sense to put the z-axis along this total angular momentum. And then we're projecting this angular momentum of the inner orbit on this vector. I can write an angular momentum as square root of 1 minus e squared, where e is the eccentricity. That makes a lot of sense because I have a radial, if I have a radial motion, right? If I throw something, I have 0 angular momentum. So if I throw something, eccentricity is 1. So 1 minus e squared is 0. If I have a circle orbit, then e is 0. And then I have the maximum angular momentum. So that is how I write angular momentum. And the cosine I comes because I'm projecting. So it's a present from the projection. And now you can see these oscillations, right? Less eccentric, sorry, less inclined, more eccentric, more inclined, less eccentric, right? When this is constant. That sounds good. To make a very, very long story short, we've shown that there is a problem. There was an error in the calculations. It was a problem in the Hamiltonian. This integral of motion violates total angular momentum conservation. And in fact, it only is conserved in a very specific system where my outer orbit is axisymmetric, so circular. And if one of my inner members is a test particle, so it cannot torque anything else. And only then it's conserved, and only then one of the approximation, remember I have an expansion, can be used. So we have set up to change this. And first of all, we rederived everything. That made a huge difference. We also went to higher order terms in the Hamiltonian, because I don't like working in a exactly circular orbit, which is most of the orbits in nature are not exact circle. So why should I confine myself to that? And that means that it allows the angular momentum to change for both orbits, both orientation and their magnitude can change. And that meant that we can tap large parts of the parameter space, because Kozai and Lidov had their work back in the 60s. And some people got excited and tried to actually apply this. It's called the Kozai-Lidov mechanism. However, the problem was that in order to get anything interesting, any eccentricity excited, any interesting inclination to be pumped up, you needed to start with the two orbits almost completely perpendicular to one another. So if I need to fine tune my parameter space, it doesn't really work. But once we actually rederived everything from scratch, we showed that there's no real need to fine tune anything. It just comes in wide parts of the parameter space are interesting. The system is way richer, and it's also chaotic, as you would expect from three-body problem. Before that, the problem was integrable. Actually, it was super integrable, which is funny. In addition, interesting consequence is that I can flip orbits from below 90 degrees to above 90 degrees. Before that, I couldn't flip because I had something cosine I equal to constant. I cannot change the sign of the cosine. So, but that was a mistake. And also we can reach extreme eccentricities, which is very exciting. If I want to merge two black holes, I can just smash them together. So that's also pretty cool. I want to show you exactly how it looks. So here you can see the inclination. Remember, this is the angle between the two angular momenta. And here it's the eccentricity as 1 minus e, because I care about pericenter passages, how close the two bodies are coming to one another as a function of time, right? So this is circular, this is eccentric. You can see here the oscillations almost similarly to what Kozai predicted, right? So inclination and eccentricity oscillates. But you can see here it's below 90 degrees, above 90 degrees, below 90 degrees. You can see also these very high eccentricity peaks. Just to make my point, this is what happened if you use the Kozai evolution. It's qualitatively different. And funny enough, the blue, of course, does not agree with any direct n-body simulations. I do want to point out the extreme eccentricities that we reach. We reach extreme eccentricities here. And we studied this and we showed that it's very prevalent in the parameter space to reach these high eccentricities. I also want to point out that I keep on writing here GR effects everywhere. So let me point to what are these GR effects and if they are important. So we know how to write the three-body first post-Newtonian Hamiltonian. This is it. So P's are momenta. They're the different masses. So this is its form, right? These people have worked it out. And there are different things that this term is doing. First of all, it can create precession, like Mercury precession, right? So this is my illustration of precession. And what precession sometimes is doing is suppressing the eccentricity excitation. So here you see my calculations one time without the post-Newtonian effects, which is in red, and one time with the post-Newtonian effects, which is here in blue. Again, inclination, 1 minus e is a function of time. And you can see that in part of the parameter space, and we know exactly to map where, based on the resonance of the system, the post-Newtonian will suppress the excitation, the exciting stuff that we want to have. However, in some other parts of the parameter space, again, we know exactly how to map it. There are all these people that have worked about this also and tried to and confirmed our findings. In some other parts of the parameter space, you re-trigger these eccentricity excitations, even with the inclusion of the post-Newtonian terms. And that is happening because you destabilize the resonance, which is kind of cool. There's also an interaction term between the two orbits, so the two-orbit process, and the interaction term between the two orbits due to general relativity that also excite the system as well. So there's a lot of cool stuff that we can do when we are now want to try and understand what happens to two black holes and if they'll merge. I want to say one more thing. This had become such a hot topic in astrophysics, and I want to relate this also to having a postdoc program, which is part of the vision that Mani has. I worked on this when I was a postdoc at Sierra. I was a Sierra fellow at Northwestern. I had the freedom to explore whatever I wanted, even though I was told never work on triples, it will kill your careers. And it seemed as if was a dead end because wasn't it solved by Kozai? So who am I who worked on cosmology to come and do something new? But I was interested, I wanted to understand it, and I found something new. And I think this speaks to the importance of having an institute like the institute that Mani visioned, and having a postdoc program that allows postdocs to have the freedom to try and do things that are a little bit risky and maybe out of the box, and try to find different solutions to problems. So again, Mani, I really want to thank you for doing this for UCLA. And here you can see, by the way, how hot of a topic it is. These are citations that mention the word Kozai. We have had our paper here. So that's kind of cool. This is partial list of people who work on this. The keen eyes among you may identify Lisa Rendell, who works on that now. And it's also a best-selling book now. So there's a lot to do with triples. But let's go back to our problem. Will they merge, right? This is how we began our thing. So here are my two black holes, and I want to understand, will they merge due to torques from the supermassive black hole, right? This is the eccentric Kozai-Lidov. This is how we call it, to try to see if, what will happen. The answer is yes. This was studied by another one of my students, Baoming Hong, who will graduate this year. And here we see the inclination, 1 minus E, semi-major axis. This includes gravitational wave emission too, as a function of time. And the blue is the Kozai nominal calculation. They never merged. And then the red includes our calculation that did merge. Baoming also did a whole Monte Carlo simulations. And this includes some uncertainties about how exactly things distribute in the beginning, and also what is the star formation rate. But given all these uncertainties, she was able to estimate that a significant part of what we observe with LIGO may be coming from galactic centers, which is kind of interesting. We did even better. We said, let's follow stars as they evolve from birth to old age, all the way to death. That gives me white dwarfs, neutron stars, and black holes. We included a lot of other physical processes. The lovely thing about using Hamiltonians is that these are additive creatures. So we can add Newtonian, we can add general relativity, and we can add other things that may be dissipative in the stage of the equations of motions, which is what we've done here with tides and even stellar evolution. And we found many, this is, by the way, from Sky Telescope featuring our work. We found many binaries, many interesting binaries. This work was done with Alexander Stefan, who since graduated and is now a Buckeye Prize Fellow and a Presidential Fellow at Ohio State University. And we also joined forces with an undergrad here. I like to work with a lot of undergrads too. This is Cheryl Wong, and she led a paper also with Alexander to try to understand that, including some better understandings of what stars are doing. And we found interesting rates. Interestingly enough, the rates are the same as what I've told you before, but then we could also give some predictions for neutron star black holes and neutron star. And that was pretty interesting. But one of the things that I think may be more interesting is try to give predictions apart from rates of what else we can see. So what I want to show here, this is from Cheryl's work. I want to show we have awesome undergrads in UCLA, and that's I have to emphasize this. There's an undergrad who worked on this and did amazingly. So everything that you see, this is what she did. Here you see the characteristic strain. This tells us by how much the effective arm of LISA, so Barry already introduced LISA, it's going to have 2.5 million kilometers arm in space, and it will be able to see on smaller frequencies. So the characteristic strain tells me how much the arm is changing because of interactions with gravitational waves. The frequency is the frequency of the wave. This line describes the estimated LISA sensitivity curve. So if I'll see something above it, it means that potentially it can be observed by LISA. Below it will not. And here are, for example, the waveforms. This is the envelope of under all the frequencies that the gravitational eccentric binary gravitational wave will be seen before it is merging, right? So this is way before. This binary is just moving about its business in the galactic center, and we may be able to see it, right? And the point is that we don't think that we need to be that lucky to see it. There is a non-zero probability to actually see it. And white dwarfs, we may see even more. And that's a huge and loud signal within LISA that will take place. But then let's say that I'll observe a black hole in the galactic center, and then I'll observe 2 black holes in the galactic center, and then I'll observe 2 black holes in the galaxy. LISA localization will not be that good. How will I tell the difference? How will I know what are these sources that I'll see? And that was another study that Balmin, that I've presented before, led. And we thought, well, let's use the feature, one of the hallmarks of the eccentric Kozai mechanism, the eccentricity oscillations, right? Eccentricity grows and goes down, and we may be able to see it within LISA. So here I'm showing the characteristic strain again, right? How much does it changes as a function of frequency. You will see things move here. There's going to be a little movie. And here you will see the eccentricity, where we are in this eccentricity oscillation. And I should note that this time interval is 1 month. So, and LISA is going to run for 4 or 5 years. So we're actually going to see things in a very short window of time. And the idea is that we will see the signal moves back and forth. If it comes from our own galactic center, it will be awesome because it will be extremely loud, and we will just see it move back and forth. We also predicted that we can see it for many black holes in the local group, and even for intermediate mass black holes. So that's also pretty exciting because it will allow us to disentangle the system. How many minutes do I have left? Oh, wow, I'm good. All right. So far I have focused on binaries that are around a supermassive black hole. But there are many other sources. There are single black holes around the supermassive black hole. I just advocated, or at the beginning I advocated, that often they'll be torn apart, those black holes. So if they're torn apart before they'll get to merge, then they're just there flying by. And this is another source of gravitational waves that we expect. And these are called EMRIs, extreme mass ratio inspirals, which are a big black hole merging with a little black hole. And that is also one of the candidates that LISA is aiming to observe. And this is from LISA mission proposal. Here I showed the characteristic strain. It's a function of frequency. This is way busier plot. I didn't make that plot, but you can see LISA sensitivity curve here as the green or the dashed black. And the lines to pay attention to are these lines, which are the EMRIs, again, big black hole merging with little black hole, that are above the LISA sensitivity curve. So we expect to see a lot of these type of black holes mergers within LISA. And I want to emphasize, these are actual mergers, unlike the binaries that we just think that we will see them go around and then eventually they'll merge within LIGO. Here, we will actually see the chirp and the final merger. And I'll just give the punchline of this part of my talk. And the punchline is that we predict that the EMRI rate in supermassive black hole binaries is much, much higher than was thought of before. And it's much higher than around single supermassive black holes. So I want to explain why. And there is kind of cute missing physics that give rise to this conclusion. So let's think first of how we form an EMRI. The idea to form an EMRI is by little kicks that take place, right? So again, I want to shoot little black holes into a big black hole. So here is a big black hole M1, and then there is a sea of little black holes. And these little black holes may be the end result of this massive star evolution that I mentioned before. These little kicks, these gravitational kicks that take place, we treat them as one-dimensional random walk, which means that on average, it cancels out, but the square does not. right? So I'm describing here square root n statistics. In other words, if I want to describe the change of angular momentum, it will, after some n interactions, it will be equal to the square root of the number of interactions times the characteristic change that I'll have per interaction. And we care about drastic changes to the orbit because that can lead us to shooting a little black hole into a big black hole. And that means that I'm looking for a change of the angular momentum by an order of itself. And I can define the number of interactions as some characteristic time scale called the relaxation time scale over the period of the orbit. And there is a way that I can characterize, and this is why I'm showing this equation, because it will play a role later on. So I know that we're in the third act, so it's usually not common to show a gun to the third act that's supposed to shoot at the third act, but this is what I'll do anyways. Practically speaking, what it does is that if I think about some critical radius around the supermassive black hole, let's say Schwarzschild radius, or a radius from which gravitational wave will take over, and I have my example orbit, after these kicks took place, I can have such a dramatic change that I'm pushing the black hole in, the little black hole. And this has long history in the literature. People have calculated this, and whether they did this analytically or numerically, they all got the same result up to a factor of a few, that the rate will be few times 10 per gigayear per galaxy. And this is what Lisa is using to try to motivate this search. But I already said that I want to talk about binary black holes. And there is a reason why I want to talk about binary black holes, supermassive black holes. So I want to put another friend to the supermassive black hole and try to understand what that will do. So you can think to yourself, but wait a minute, why are you talking about supermassive black hole binaries? And the answer is because it's a natural consequence of galaxy evolution, combined with the fact that almost every galaxy hosts a supermassive black hole at its center. So we expect that supermassive black hole binaries will be something common in our universe. We have also some observations that may allude to that, but theoretical plus observational argument seems to point to that fact. All right, so now if I have a supermassive black hole binary, and one thing, you know, I occasionally work on triples, so no one laughs for my jokes today. That's really bad. We expect that the eccentric Kozai-Lidov mechanism will work on that. And there have been some people who worked on that, even us, but it wasn't very exciting. It didn't seem like it can produce a lot. And the main problem was the general relativity precession suppressed eccentricity excitation, and that was kind of boring. But I mentioned a missing piece of physics. And the missing piece of physics was, where is the two-body relaxation process? Why didn't we include it so far? And there is a reason why we haven't. And this is something that often in dynamics, when we have multiple physical processes taking place, we do. To know from theoretical arguments what I should take into account, I'll look at the timescales of these physical processes. So here is a timescale. This is distance from the supermassive black hole in parsecs. You can see here the eccentric Kozai-Lidov timescale. You can see here the 1 PN, the first post-Newtonian precession timescale. If I want to have any eccentricity excitation to take place, I need to be in this very tiny part of the parameter space. Boring. You can also see here the two-body relaxation in black. It's so long compared to all the other processes that we just neglected it. But I think that was a misleading argument. And that alludes to the equation that I showed you. The changes in angular momentum goes like the square root, not like to the power of 1. So if I look at how the changes to the angular momentum take place, and this here I flipped it so it will be easier, than the time will be in the numerator. You see here angular momentum over the change of angular momentum as a function of distance. And you can see that the two main actors here start now to overlap. That means that two-body relaxation needs to take a bigger role. So let's test it and let's see if it works. So here I'm showing the semi-major axis, which is here the line, and then the pericenter passage, so how close things are. This is the wiggly line here. This is the inclination, and the two angles, these are Euler angles that tell me how the orbit is tilting. There's something cute there with a resonance. This is why I show it. It's okay. And as a function of time. This only includes general relativity and EKL. So now I will turn on two-body relaxation, and you can see that I was able to form gravitational wave sources this way. This is the blue. The gray did not, the blue did. You may ask yourself, well, maybe I could just have done it with two-body relaxation on this time scale. This is the red. It did not. We worked through a process of doing a Monte Carlo to try to estimate how often it happens. I will not show you the plots. I'll show you a cartoon instead. What happens is that basically all the black holes are coming inside like that. So we're sweeping all the black. It's extremely efficient. And the reason that it's extremely efficient is because the two-body relaxation, these little kicks, are moving my black holes back and forth to a more EKL, to more eccentric Kozai-Lidov sensitive place. So it's more favorite place. So we're getting raining black holes. Hallelujah. I will just finish by saying that when they come in, they're staying on the ergosphere a little bit. And there are some interesting trajectories on the ergosphere. We know that a test particle in an ergosphere will zoom around and will, this displacement is just for illustration, but it zooms around the ergosphere. But now I have a little black hole coming on the ergosphere, right? And it will spend some time there. So I may be able to see it more than just a burst. It may actually completely change its trajectories. So some of this part is already known, especially if I'm bringing something from close by to the ergosphere. Ergosphere is, sorry, I should have explained that. Ergosphere is this pseudosphere that takes place. It's not a sphere, it looks like an egg that takes place, or football. I think football is better. Me and shapes are okay. And then it makes test particles, rotate because it's rotating the entire space-time around the rotating black hole. And here we show the time you spend in the ergosphere versus the time that you would just estimate this if it would have been a Newtonian calculation. So you actually spend a lot of time. So you have a lot of time for gravitational wave emission to work and change the trajectories. And that's the rate. So here, this is the rate that we expand using all of the uncertainties for two-body relaxation plus EKL plus GR plus gravitational waves is a function of the mass of the supermassive black hole mass. And this is what people have assumed around a single supermassive black hole. And I like it so much because it allows you the opportunity to disentangle between different physical processes, between single supermassive black holes and binary supermassive black hole, right? We estimate that maybe there are a lot of them, but we don't actually know, right? So if LISA will be as awesome as we all hope that it will be, we will be able to disentangle something very fundamental about our universe. All right, so I hope I convinced you that triples are awesome, because in the right configuration, you can go all the way even to the moon. And I showed you that we have new understandings of what the triple body dynamics is actually doing, and that can lead to black holes, neutron stars, and white dwarfs mergers at the center of galaxies. And these are very natural places to find gravitational wave sources. We also showed that we can disentangle different type of mergers based on LISA or predicting for LISA observations. And lastly, I showed you that apart from black holes, binary that will result in gravitational wave sources, we also expect a lot more little black holes merging with a big black hole in a supermassive black hole binaries. Thank you, Mani, and happy birthday.
talk. Questions?
Okay. Lunch, we're all very hungry.
Yes, yeah, thanks again. And I guess we'll reconvene at 2 o'clock.
Thank you.
Why do people use the wrong sign? I didn't notice that one.
Yeah, it comes from